object have a size of around 50 nanometers.
Sorry, this is a two-dimensional picture, meaning that these points are what?
It's two-dimensional, so they are
cross-section of
you go through the sample. They are like tubes. So skyrmions are named after Skyrm, and originally Skyrm developed a model in the context of nuclear physics in 1962. He was actually inspired by Lord Kelvin's works on, in particular, this publication on vortex atoms. Kelvin himself was inspired by Helmholtz's work on vortices in fluids, and he was working with Tate, and they were observing smoke rings and their interaction, and the idea that atoms could be knots in the ether, and they started to do a classification of knots, which motivated some first work on knots theory, which later became part of topology. So to illustrate this, I'm showing you another example, which is happening. It's a recent publication, and this is some representation of Hopsian topological excitation, which you can represent the core of these vortices, and you can see here example with different topological charges. So in the case of my work, we are working in the micromagnetic modeling framework, so it's a continuum mesoscopic theory. So we are looking at magnetization fields, which have the properties to have fixed modulus. So this is an example of a typical energy functional. So the type of term we have is exchange, which makes the system ferromagnetic. It wants to align the spin. Then we have some magnetocrystal anisotropy, which wants to align the magnetization along certain direction. We have the Zeeman, which is interaction with an applied field, which also aligns spin together. And we have a magnetic dipole interaction, which wants to have spins anti-parallel. It wants to, it's in competition with the other energy terms. And I want to remind that in magnetostatics, we can represent the magnetization by what we call magnetic charges. It's a convenient way to represent magnetization, and you obtain some surface charges, and in case when the magnetization is non-uniform, some volume charges. I'm going to talk sometimes about magnetic charges in the rest of the talk. But let me start by defining this topological degree of a field and give some example. So the topological degree is a degree of a map. So I take a map from a manifold to another manifold of the same dimensions. And what are the images in P, and xk are the pre-images, and the definition of the degree is the sum over all the pre-images of the sign of the Jacobian. But okay, I will give a simple example in 2D. So I consider a magnetization field along a line, and magnetization can turn in the XY plane, and it has to point up at infinity. It has to be sufficiently compact for this to be well defined. But okay, this forms a knot, so you cannot get rid of it without cutting, and you can project it on a circle, and this is what you get. And this is the definition for 1D. This I get a +1 degree. If I wind this thing in a different way, if I turn clockwise and then counterclockwise, I don't form a knot. I get 0. And last example, I can wind counterclockwise. In that case, I will form this type of rotation, and this is degree -1. So now we are going to consider the 2D case today. And in that case, the magnetization can rotate in the 3 dimension. And we have these two angles, phi and alpha. And if they rotate in the same direction, I get degree 1. This is what I call a skyrmion. And there is also an anti-skyrmion in the case these two angles rotates in different directions. Okay, so there are all then other possibilities for this rotation. This is what we call near skyrmion, block skyrmion, but they are intermediate angles. And there are also a lot of possibility for anti-skyrmions. So let me give you an illustration. In fact, there exists some magnetic skyrmion excitations in a two-dimensional isotropic system. So it's a system without anisotropy, which can be described only with this energy term. And this is some electromagnetic simulation that is done by starting with a random state. And you see the formation of domains, but also a lot of this skyrmion and anti-skyrmion that you can characterize here by plotting the 2D topological density. And you see the apparition of white and black dots, which correspond to this excitation, and they run the simulation, they will have a tendency to collapse. So these things actually exist. In particular, there have been a lot of studies in quantum Hall system in the 90s, and they indirectly measured their presence in spin polarized 2D electron gas. And there is a signature of their presence by a decrease of the spin polarization near the Lambda level. Okay, so from the point of view of the theory, there is an important paper from Baylor from 1975. He was working on classical 2D Heisenberg model. At that time, there was some important work on phase transition on the XY model, and Baylor demonstrated the existence of scale invariant topological non-trivial minimizers of the exchange energy, and this has some implication on phase transition in ferromagnets. So he proved the existence of a sharp lower bound for this energy, which is 8 pi times the degree. And there is an explicit profile for the solution. And this is also scale invariant, so the energy doesn't depend on the size. So, but we are interested in a uniaxial ferromagnet. So we are adding an anisotropy term, and this will destabilize this skyrmion excitation. Actually, it was shown in this paper rigorously that the solution is unstable under this condition. And this paper is actually a comment on another paper where this guy has the intuition of the existence of this particle, but it wasn't proved yet, and it wasn't known which energy will enable their stabilization, because you need other energy term to stabilize these skyrmions. And today I'm going to talk about two of these energies. One is the well-known dipolar interaction, and another one is a more exotic interaction called Jaroszewski-Moria. So let me, okay, so first, they are acting on different length scale. The dipolar interaction is known to act at long range, while the Jaroszewski-Moria interaction is a local interaction. So I will explain later in more detail what is this Jaroszewski-Moria interaction and where it comes from, but let me show you some example. So the dipolar interaction is stabilizing what we call magnetic bubbles. So this is on the right, you can see the first images of magnetic bubble, which is obtained in materials called garnets. And these images are transmission optical microscopy. So this is what we call the Faraday effect that allows us to observe the magnetic domains. On the right, it's an example on the cobalt monocrystal. And there it's electron microscopy. And you can see that these bubbles appear in black and white. It's because they have different topologies. So they don't have the same rotation in their wall, and that's why they appear with these different colors. It's an important point because we are going to see that there is another type of this object that have always the same topological degree, and this is this one that we call skyrmions. So these objects are cylindrical magnetic domains, and they were studied a lot between the 60s and the 80s, because they wanted to make magnetic memories out of them. So at that time, they did some full phase diagram to show where this bubble would have the right size. So this is a video of such magnetic memories that were developed back then, but they turned out to be too costly because you had to apply a rotating magnetic field to move them. So it was very complicated. Okay, so more recently, there's been an observation of what we call compact skyrmion. So this object can actually have the same size as the magnetic bubbles, but here there will be a homochirality, so it will always show the same rotation. So this is a characteristic of the Jelusinski-Moria interaction. So let me explain what is this Jelusinski-Moria interaction. So in fact, Jelusinski was trying to explain why a very weak magnetization is measured in certain iron oxide compounds, despite the fact they are magnetic. And it just had the idea, it's a phenomenological introduction, just by symmetry argument, that if there would be such a term, then it will favor a canted arrangement of spin, and it could be an explanation. Later on, Moria justified this assumption by developing what is called an anisotropic super-exchange interaction. Super-exchange interaction is an interaction between two magnetic atoms through a non-magnetic impurity or atom. So he was able to give a parametric expression of this parameter in function of a physical parameter, and he showed that this type of interaction is expected in all kind of non-centrosymmetric material. It was later shown that when you have a non-magnetic impurity in a magnetic metal, there are all this type of interaction also plays a role, and you can also see an interface as an impurity, and in the case of a non-symmetrical interface, you obtain a chirality. That is something that is favoring a given chirality in system, and it reduces the energy for rotation of the spins. So the theory explaining the appearance of these patterns was developed in the case of magnetic bubbles in the 1960s, at the same moment as they were observing these objects. And it was only in 1989 that there has been a prediction of the existence of skyrmions. Back then they were called magnetic vortices. And it's only 20 years later that these objects were observed for the first time. So to give you an idea of where this solution comes from, I show a simple model in 2 dimensions. And what is important is that we define a non-dimensionalized DMI parameter, a non-dimensionalized anisotropy. And here you see a model where we have exchange, anisotropy, and DMI. And so you can assume that the solution is axis symmetric, and you just have to solve a boundary value problem of with Dirichlet boundary conditions, which are spin down in the center and spin up at infinity, for example, and you get such a profile for the skyrmion rotation. So in fact, here there is only a local part of the dipolar interaction that is taken into account. This is what we call the shape anisotropy. It's very important because this is of the same order as as Q is of the same order as 1, so you just can't neglect it. However, the long-range dipolar interaction that is stabilizing the magnetic bubble was neglected in this theory, and there is no justification of that apart from the fact that there are technical difficulties to take into account these long-range interactions. And the existence of magnetic bubbles, which are very similar to skyrmion, is a strong indication that both of this energy may be playing a role in it. So in 2018, I worked on to explain, to predict B stability between the skyrmions and magnetic bubbles. So I developed a phenomenological model that was taking into account both DMI and the long-range interaction. And I predicted the coexistence and transition between the skyrmions and bubble, which is happening through what we call the bursting and collapse phenomena. And this was also demonstrated in parallel via ansatz-based numerical calculations. But today I'm going to present another work where we more rigorously calculated this long-range effect on the compact skyrmion solution. So we didn't look at the bubble, we were concentrated on the skyrmion itself. And we showed that the skyrmion can actually be stabilized even in the absence of the Rushinsky-Moria interaction, solely by the dipolar interaction. And there is a parallel, let's say a twin work where you will find more detail on the mathematics, and where there is also a quantitative rigidity result of degree plus minus 1 harmonic mile from the two-dimensional sphere to it. So we take the same model and we are going to restrict ourselves in a low kappa regime where isolated solution exists. And now we have a new non-dimensional parameter, which is the thickness. And it also has to be small in order that the magnetization is independent in the Z direction. So it's a two-dimensional model. And now we are working with the full dipolar energy. So this was the classical theory, and we are adding the dipolar energy in the whole space. And working in this thin film regime, we are expanding in the Fourier space, and we are obtaining these three terms. So the first represents the local dipolar that was taken into account before. And we have two new non-local dipolar terms, one corresponding to what we call surface charges, which will lead to a decrease in the energy and stabilizing the skyrmion, and another one which represents a cost and which is related to volume charges. So this is our energy, and this in itself contains a lot of things. So it can describe the ferromagnetic state, the strike state, a bubble lattice, the helicoidal state, etc., etc. We want to focus on one thing, which is an isolated compact skyrmion solution. So we need to define a restricted class in which we are going to work, which is saying that first we need to have the magnetization pointing up at infinity in a sufficiently compact way, and we are fixing the topological degree to be 1. We also have a topological bond of 16 pi, and this is because of this topological lower bond that I talked about before. This will allow us to exclude the splitting of the skyrmions into two skyrmions. So we first obtain a theorem of existence, and for us physicists it is very important because this is telling us where we can actually be sure to find and where we can't find these compact skyrmions. So, for example, here I know as function of the magnetization and anisotropy that my skyrmion exists in a regime which is not very far from the transition to in plane, because that's where the energy for the formation of the rotation is lower. In fact, this is a bit the same as what was found in the past for bubbles. The ideal regime for stabilization of bubble was also along this line of transition to the plane. So this is the first result. And so we go on because we want to know more about this skyrmion solution. And what we know is that if the kappa and delta are 0, the minimizer are given by what we call the Baylor profile, and also with rotation, dilation. And we also proved that when these parameters are going to 0, the profile converges to this. So this is our starting point, but we have to modify this profile because there is a blow up of the anisotropy energy. And so we introduce a cutoff in the tail. So we define this function, which is the modulus of the in-plane component of the Baylor-Polakov profile. And then we introduce a truncation that looks like this. It decays exponentially. Okay, so using this and that, we can minimize and obtain the optimal angle and radius for skyrmions. And what we predict is that when the thickness and the DMI is varied, we have a transition from what is called a block configuration to a nail configuration. And this is expected because there is a competition between the DMI and these surface charges, which, or in the case of block skyrmion, there is no volume charges, while so when the delta is large, it favors a block rotation. But when you introduce DMI will favor the nail rotation. So there is a competition between these two due to the presence of the volume charges. So the same effect also exists for, not for compact skyrmion, but straight walls. It was shown that there is a reorientation from nail wall to block wall when you modify the DMI parameter. And there is an expression for this, and we show that in case of nail skyrmion, so the domain wall is like folded and it concentrates the volume charges, so which makes that the threshold to have a nail skyrmion is 3 times larger in case of skyrmion compared to a domain wall. So we also carry out some simulation using conventional tools because in my community they better understand this kind of simulation because they are used to them, and for them the mathematical part is more difficult. So we always do that, and we were happy to see that there is a good agreement. Because we obtain here what you see the intermediate and this confirms the existence, the fact that the threshold is increased compared to nail wall, because here at 5 nanometer thickness we still have an intermediate angle, while it should be 10 nanometer for a straight wall. So we also obtain the skyrmion radius and energy. And I'm going to tell more about this energy because from the point of view of the physics, it's very important because it tells us whether these skyrmions are stable or unstable, and this is very important for application. So, so I can actually plot the energy of the skyrmion as function of the dilation factor, and this is very important to understand the stability. So here you can see a minimum corresponding to the equilibrium skyrmion radius. And so when you shrink it, you will see an increase of energy, and it reaches this 8 pi, which is the zero radius energy. So here in gray, I represent the fact that in a real system, you hit the limit of atomic distances and the model phase, but we are working far from this situation. There actually exists another energy barrier. You can see that there is an existence of a saddle on this side, and our theory gives expression for both the skyrmion and the saddle energies. So this is important to predict the stability. In particular, so the bursting phenomena is happening when the skyrmion size is increasing. For example, imagine there are some thermal excitation. So in the case where you apply a field parallel to the core, this thermal excitation could lead to the disappearance of the solution and the reversal of the layer. So this bursting was predicted only by a numerical calculation, and we extended our model to applied field, and it provided the first theory on skyrmion bursting. So this is very interesting because it could constitute the hidden phase of the skyrmion phase diagram. So this is the hysteresis loop. So this is magnetization as function of applied field. So when you apply a strong field, the skyrmion disappears. You have a saturated magnetized state. And in this sample, when you turn off the field, you observe helicoidal state or stripe state. So it's always demagnetized. And because of that, you can never really you can only apply a field parallel, anti-parallel to the skyrmion core. You can never apply it parallel. However, we showed that this skyrmion exists even for low DMI and low delta, and in that case, they could be what we call the ferromagnetic state even at zero field. And in that case, you could apply a field parallel. And applying a field parallel to the core, of course, will favor the growth of skyrmion and stabilize them. So when we introduce Zeeman term, you obtain a new effective parameter H bar, and it's just renormalizing the anisotropy. So this is a representation of the energy barrier for the collapse and the bursting. And you see that they vary oppositely. So as a consequence, the optimal stability to have both barrier larger than a certain value is happening at intermediate value. And this is going all the way down to kappa equals 0, which means that the parallel fields can be used to stabilize this skyrmion. And this wasn't the case before in model and system where the dipolar interaction is cancelled by the thickness being 0. You don't have solution for low kappa, so you can't use this to stabilize skyrmion. And we carried out electromagnetic simulation to further confirm the existence of this field stabilized solution. So this is the skyrmion radius as function of gyration schemoria and applied field for field applied parallel. And as you increase the DMI, there is again reorientation of the skyrmion angle. So what we get from the numerical simulation is interesting. Actually, we are looking at outside the range of validity of our model, because actually our model is describing compact skyrmion, and as you increase the size of the object, either by applying a field or cranking up the DMI, in fact, the profile will be different from Baylor in Polyakov. So the solution will still exist, but it will disform, and at some point it will burst. So what we observe here is an increase of the radius and the bursting. And what is important is that there is a good agreement with analytical theory along this line, and we indeed observe a bursting, and we have solution going down to 0 DMI. In terms of the skyrmion angle, we see here also reorientation towards the block rotation at 0 DMI. And what you see here is also expected. What is up? So I told you that for a straight domain wall, you get an L rotation and less DMI than for a compact skyrmion. Because for a compact skyrmion, the volume charges play a stronger role. So here what we can observe is that as you grow the size of the skyrmion by applied field parallel, we have a transition from, let's say, the compact skyrmion to something looking more like a bubble. And here, the energy of the wall is more closer to the one of a straight wall. So we have a reorientation from like 45 degree to a 0 degree wall. So to summarize, we developed a continuum micromagnetic theory of compact skyrmion taking into account the full dipolar interaction. We prove the existence of this isolated skyrmion for even random parameter, also showing that this can stabilize in the absence of the DMI. We obtain explicit formula for the energy and size. And we predict a new regime where the fields could play the same role as the DMI to stabilize skyrmion in the low DMI and large thickness regime. And just quickly, I want to show you that in my spare time, I'm also doing some experiment where we observe in ultrathin, like 2 monolayer cobalt systems, some stripe domain and skyrmionic bubbles. And we are working to control the nucleation of these skyrmions with applying an electric field here through a transparent electrode. And we can also control the stripe domains. So here the sample is in some kind of superparametric state. And when we decrease the applied field, we obtain these stripe domains where there is a lot of thermal activation that allow the states to demagnetize. And when we further increase the electric field, we are, in fact, we are increasing the DMI, and the system try to rearrange into a larger periodic state. And now I want to thank my collaborators, Teresa Simon, and we also did an extension of this work where we calculated the lifetime of skyrmion with Valérie Slastico.